My name is Chris Celio. I'm a graduate student at UC Berkeley, advised by Chris Dosanovich and David Patterson. And today I'm going to be comparing a handful of different instruction set architectures against one another using the industry standard SPECint benchmark suite. And let's just see what happens. This is a companion to a tech report that we just released, where based on this data that I'm going to present, we're going to make a renewed case for reduced instruction set computers. If you like my talk or you want to see more data, please go and give that a read. And if you don't like my talk, you should still read it anyways. I do want to define my terms. Today I'm talking about comparing instruction set architectures, ISAs. That's the boundary between the software and the hardware. I like to think of that as the language that the processor speaks. To make that explicit, if you have some source code for an application you care about, like bzip, you tell your C compiler, please target the RISC-V RV64G instruction set architecture. And once you have that binary, any processor that can speak RV64G can run that binary, whether it's a single issue in-order core like Rocket or the superscalable core like Boom. The user will not be able to tell what microarchitecture is implementing their program. So to be clear, the instruction set architecture is not a processor. Even Wikipedia gets that wrong all the time. For our comparisons today, we're going to be looking at 6 different instruction set architectures, 2 from Intel, 2 from ARM, 2 from RISC-V. For RISC-V, we'll be looking at RV64G. That's a 64-bit general purpose ISA, boots Linux and all that good stuff. We'll also be looking at what happens when we take the compressed ISA extension. It's be the same code generation, just instead of all instructions being 4 bytes, they'll also include 2-byte forms of the most common instructions. I also want to clarify here, these are all 6 completely different instruction set architectures. When you go from, say, 32 bits to 64 bits, as NVIDIA was talking about, it's a complete new ISA rewrite. So it's an opportunity to throw away a lot of the warts and sins you've committed. So going from, say, RISC-V to ARMv7, they double the number of general purpose registers. They fix up a lot of the different aspects. These are all different instruction set architectures. As I said, this is based on a tech report where we kind of make a renewed case for RISC, for reduced instruction set computers, the idea that simpler is better, simpler is faster, as a counterpoint to these complex instruction set architectures. It's a long simmering debate, and there's a couple of conventional wisdoms that have distilled up to the top. One is that these complex instructions, you can describe multiple operations in a single instruction, and you can describe you only need to use as many bits as you want to describe that instruction. It's a variable length ISA, which means that you have more expressive, denser instructions. With RISC, RISC instructions map very well to high-performance pipelines, so it's really easy to make these go fast. But then the CISC guys did a bit of a jujitsu and realized, wait a minute, we can just on-the-fly decode or retranslate our CISC instructions into RISC-like micro-ops. So we can have both the expressiveness and the density and get the high performance. And this is what we've seen borne out in the marketplace. You have the CISC ISAs from Intel has dominated the desktop and server spaces. And we also have the CISC ISAs from ARM have dominated the mobile and the embedded. So my claim is that a well-designed RISC ISA can actually be very competitive with CISC ISAs. In particular, a well-designed RISC ISA can be denser, fewer instruction bytes per program, and higher performance, fewer operations per program. We'll see if the data bears that out. To my last point about ARM, can anyone tell me what this instruction does? It's really simple, just sound it out. I have 260 people here and no one can tell me. Amazing. This is, it's pretty simple. Just a straightforward load multiple, increment the address. So it's going to perform 6 loads, right to 7 registers. That 7th being the operand, it's going to side effect. I think that's what the exclamation point means. It's very excited to do this. The EQ means that not only is this a load multiple, it's also going to perform, we may not actually perform it based on some implicit processor state. In ARMv7, you can write to the PC, which means that not only is this a load multiple, it's also a jump. And because it's execute under a condition code, it's actually a conditional branch. So that's very exciting. This is also not something that I just kind of found hidden away. This is, at least the non-conditional form, is an incredibly common idiom. This is actually how you do a stack pop and return from function call in one instruction. So I'd argue that ARMv7 at least is a pretty CISC ISA. x86, that's all I got to say about that. Oh, yeah, I'm not going to spend time on this, just that this is a cool instruction. There is the pseudocode. I found it a bit hard to fit that on one slide, whereas with RISC-V, we can fit the entire ISA on one slide. Okay, so what's my motivation for collecting all this data? It's a bit of work. Why do this? So as my day job, I work on building the Berkeley out-of-order machine, RISC-V out-of-order superscalar, parameterizable. It's open source. You can download it, play with it, check it out. Tell me what you think. I accept pull requests. And when I tell people about this, they go, OK, that's nice. How good is it? You know, what's its core mark score? What's its spec score? OK, so I can download those programs and run them, and I get some sort of seconds to run core mark, and I can run it on ARM and get the same. And what I find out is, OK, this particular version of Boom is 30% faster than Cortex-A9, and this particular version of Boom is 2% faster than Cortex-A15. Is that good? Like, I don't know what to do with that. Does it mean I need to work harder? Do I need to be fired? Or can I graduate? Like, I don't know. And to explain why I'm confused is I'm measuring the raw performance, seconds per program. But there's actually 3 specific terms that make up performance. And as the guy building the processor, the microarchitect, I only have control over 2 of these terms. How many cycles to execute an instruction, how many cycles there are a second. Technology, but that's kind of normalized across all these processors. I don't have control over this last term, how many instructions there are in a program. That's controlled by the ISA. And so I said, OK, well, if Boom is doing worse than an ARM core, is that just because I have to execute more instructions and it's just a bad ISA? And if Boom is doing better than an ARM core, is it being held back by a bad ISA? I don't know. So I wanted to figure out what is the real quantity of this term. So our goals here today is to get a baseline to measure the current GCC quality of the RISC-V port. And once we have this data, there's some other things we can learn. And given that the RISC-V user-level ISA is fixed, what can we do to make the compiler better? Given a fixed user ISA, what can the programmer do to improve their performance? And given a fixed user-level ISA, what can the microarchitect do to improve the performance of the processors? And the last one's what I'm going to focus on here. I should also clarify my non-goals. I'm not showing this data here to try and make arguments for adding new instructions. There's a lot of due diligence required that I'm not going to go into, and hopefully no one uses my data against me. But you have to think about the verification cost, the time to market, whether the compiler can actually use these instructions. I'm also, and if it sounds like I'm lobbying for instructions later in the talk, don't listen to me. And this may be hard to believe, but I'm also not trying to actually make any claims about relative ISA merit. Everyone today gets a participation trophy. They're all just trying to run C code anyway, so how different could they be? But we also have to take a step back here and have a little dose of reality. None of this matters if you're 10 or 20 or 30% off, or even more, if your application is missing in the cache, or if you're just spending the whole time spinning on user input. The other thing is that if you're looking at the instruction count, that can actually be incredibly misleading. So let me dive into that point a little bit more. The first reason why you may see a very low instruction count, but that's actually not really a good qualifier of how much work is being done, because you may actually take one instruction and then generate multiple micro-ops to implement that instruction. So let's talk about maybe Arvin's favorite instruction, the repeat move. You're going to be, this is the memcopy instruction, so it's going to repeatedly move up to some C words from one address to another. Going to perform a lot of side effects. Imagine what happens when you have an exception here. It turns out your instruction may only partially execute. This is a pretty complicated way, but this is how you do it. And you're trading off, you're having a lower instructions per program, and you're paying for more cycles to execute that instruction. So that's one way we can be misled by the instruction count. And the other direction is macro-op fusion. So we can actually have a lot more instructions than we actually really have to execute. So we can actually take multiple instructions and fuse them on the fly. As an example, in RISC-V, we have a full register-register magnitude compare and branch instruction. That's a single 4-byte instruction. I had no idea this is actually a fairly uncommon instruction in ISAs. For ARM and x86, these are 2 instructions. One, the compare that sets the condition code, and then the second instruction branches based on that condition code. Now that may sound horrible to spend 2 instructions on every loop, but in actuality it's not that bad. You just lie to the decoder, tell it every time it sees a compare followed by a branch, and it's just a single larger instruction. So this is how they get around some of these ISA quirks. So those are the 2 ways that we can be misled by the instruction count, either inflated or deflated. Let's ignore that and let's talk about instruction counts. So for our ISA shootout, we're going to compare 6 different ISAs. We're going to measure the instruction counts. For x86 64, we can also look at the micro-op count that the processor can tell us, so we can get a better feel for how much work an Intel Xeon has to do. And we're also going to look at the number of dynamic instruction bytes, how much raw bytes that we have to fetch to execute the ISA. We're going to use SPECint today. This is 12 benchmarks across 35 workloads, 20 trillion instructions, so that's about an hour to run on an Intel Xeon, and about an hour to compile on an ARM core. We'll be looking at the workstation workloads. This is lots of data, lots of compute, not a lot of data generation, and no idle periods. So we have to also be aware that we are looking at a very specific set of benchmarks. And for RISC-V, and for all of them, we'll be using glibc and running on top of Linux. We will be using GCC 5.3-03 for all of these, so we have a nice clean baseline. The compiler version that you use is actually really important. I think just moving from 5.2 to 5.3, I saw a 3% decrease across the board. So you can sometimes see bigger differences between compiler versions than you see between instruction set architectures. As a point, we don't have a vectorized say extension in RISC-V yet. And what our interest today is in comparing scalars. Unfortunately, it's really hard to remove Intel's SSE SIMD from your binary. On the plus side, it turns out it's really hard to get it to actually use it properly. So for this, I just use march native, M2 native, 03, and there's almost no SSE whatsoever in the binary. I will mention the one example where there is some generation. So this is how I compare scalar ISAs. I'm going to run on real hardware. I'm going to use perf to measure it, and I can also get some histograms using Intel's pin tool. On RISC-V, we can use Spike to count instructions, and Spike actually natively will give you a histogram built in. So that's a really cool tool to use. So here's the data. I'm just going to run through this. You can look at this online afterwards. I'm normalizing to x86 64. These are the two Intel ISAs. The ARM ISAs are more instructions. And RISC-V is 16% more instructions relative to x86 64. 16% more instructions. Now, I'm only going to highlight the two worst ones. GCC, a lot of that's a mem set. So that's the one place where x86 64 uses 128-bit SSE moves. That's the only place it really showed up. For H.264, it's dominated by a mem copy. That's where that repeat move instruction comes in to do a lot of work. However, like I said, we can look at the micro-op count, and it turns out, even though we're 16% more instructions, on the micro-op count, we're about even. We're about 1% off from x86 64 on the amount of work done. So if I could kidnap the Intel design team and blackmail my way onto Intel fab time, we could probably build a processor that works just as high performance using RISC-V. And I'm going to come back to ARMv7 or to ARMv8 later. Don't worry, we'll take care of them too. So let's look at the dynamic instruction byte counts. Now we can add in the compressed ISA. It's the same code generation, same performance, just we can add in some 2-byte instructions as well. And we'll look at the histograms to kind of count how much they were fetching. And what we find out is that with the compressed ISA extension, RISC-V wins on 9 out of the 12 benchmarks in terms of the raw instruction bytes per program. And 2 of those 3 is the mem set and the mem copy that we talked about. I don't know about you, but that's really impressive to me. And this is particularly interesting because in terms of 64-bit land, there's even fewer compressed ISAs to compare against. So we're 23% more instruction bytes without the compressed extension. If we add in the compressed extension, we're 28 fewer bytes than ARMv7. We're 8% fewer instruction bytes on average than x86 64. Part of this is because I was quite surprised the code density of x86 64 is actually pretty bad. It's about 3.7 bytes with a high variance. So for many of the workloads, it was using more than 4 bytes on average. Maybe they should have kicked into another RISC ISA or something. For the compressed ISA, we're averaging 3.00 bytes per instruction. So that's really pretty impressive. So this is a RISC ISA that is denser than the other CISC ISAs out there. OK, so why are we 16% more instructions? To cut to the chase, the most common idiom that I see is reading from arrays. So let's say you want to access an element in an array. In RISC-V, that requires 3 instructions. 1 to scale up the offset to the data type, 1 to add it to the base address, and then the 3rd to load. Another ISA is that this is a single instruction. Complicated instruction, but a single instruction. Another pattern that I saw, if you write your code wrong and you use unsigned 32 ints, the ABI wants signed 64-bit values. And so you end up sometimes in red having to spend some instructions to clear the upper word of a 64-bit register. So this is what happens when you don't use size T when you're accessing things in arrays. And something like ARM or x86, they're actually able to access or subfields of a register, so they can do this in fewer instructions. Okay, so based on that information, what can we do to build a better RISC-V? Well, the answer is obvious. Let's just add an indexed load instruction to match the behavior of the other ISAs. So, add 2 registers to perform the load. You could even build in the shift. And what's great about this instruction is it's a trivial addition to any RISC pipeline. We're only going to have 2 operands we want to read. We're only going to perform 1 write back. It's going to have the same side effects as the regular loads. This is great. I mean, don't you want 5% fewer instructions? Okay, let's take a step back. What we're trying to do here is we have these 2 instructions, an add followed by a load. This is an 8-byte sequence in our code. And our proposal was let's turn that into a single instruction that's only 4 bytes in size. But we have this compressed ISA, and we have macro-op fusion. So suddenly with the compressed ISA, the add becomes 2 bytes, and then the load becomes 2 bytes, and they're sitting right next to each other. Well, we can just lie to the decoder and tell it you have index loads. So this is great. We can get index loads, and we didn't have to change the ISA to get it. So if we take this idea even farther, there's a couple fusion pairs that I'm going to propose that show up in SPECint. One is the load effective address, so it's a small shift by an add, or the index load and add by a load, or the clear upper word where we're going to zero out the upper 32 bits. And we can analyze the histograms of RISC-V to see how often this shows up. And what we find out is that these idioms account for over 10% of the instructions, which means that you can effectively lower the instruction count by 5.4%. So before, we were already 8% fewer instruction bytes than x86 64, and now, when we compare the the micro-ops, we are now 4.2% fewer operations than x86 64. So here we are, a RISC ISA that is denser than the other CISC ISAs and is fewer operations. It'll be higher performance. So this is not what I was expecting when I was taking this data to see this kind of an outcome. Okay, so what about ARM? First of all, we don't know the micro-op count, so it's a bit harder for me to say exactly where their performance would stand. And also, ARMv8 runs on a wide variety of microarchitectures, both very small microcontrollers, very big superscalar out-of-order cores. So the decision that you'll make on how you implement the ISA will be different anyways. So we don't know the micro-op count, so let's guess. And I wanted to zero in on some of the complex memory instructions that are in ARMv8. So they have the load pair and a load increment address. That requires 2 write ports to your processor. And they also have a load pair increment address that requires 3 write ports. And it's common for high-performance pipelines to decide, let's actually break this up into micro-ops, and each micro-op can write at most one register. And so if we do that, we modify QEMU to count how often this happens, and we assume 1 write back at most for 1 micro-op. This will add 4% to the effective instruction count of ARMv8. So we take RISC-V. That was 9% more instructions to start with. But with Fusion, it's already fewer bytes. With Fusion, RISC-V lowers by about 5 to 6%. And if we look at the micro-op generation, ARM increases by 4%. And they basically meet about in the middle. So essentially, RISC-V is the same number of operations as ARMv8. Now, you might say, okay, but you could brute force your way through those load pair, load increment. You could add 2 or 3 write ports. But the beauty of macro-op fusion is we can do the same thing in RISC-V. We can take 2 loads back to back in a program and fuse those into a single micro-op if we're willing to pay the complexity in the register ports. So basically, we can match ARMv8 performance 1-to-1. This is not just an idea for superscalar out-of-order processors. We can even add this to, I think macro-op fusion should be used by all RISC-V cores. I think this is something that everyone can benefit from. So we can take, for example, the Rocket open source single issue 5-stage in order core. And you don't even need the compressed ISA, by the way, for this to work. You can still use macro-op fusion on the regular RV64G ISA. And so we can say, okay, instead of fetching 1 instruction cycle, let's fetch 2. And if there's fusion that's possible, great, we'll fuse it, send it down the pipeline, and then increment the PC by +8. And if we can't, then we'll just send the 1 instruction down and then wait for the next one on the next cycle. And there's a whole slew of macro-op fusion pairs that you can look for here. I talked about index loads, clearing upper bits. There's a whole slew of OWPC as well as LUI based idioms that you can fuse that are very trivial for any pipeline to do. Turns out that 3-operand adds are actually pretty fast. You could even be fusing back-to-back adds. And you can also do other things like your load pair, your store pair, your post-increment addressing, all of that great stuff. And what's really neat about this is that Rocket only has one write port. So you could just say, well, you know, I'm not really willing to add a post-increment load to Rocket because that added an extra load write port. But you could add the store address increment because that only needs the one write port that you already have. So you can actually be kind of asymmetric on what kind of optimizations you want to make to the processor, and you don't have to touch the ISA to exploit those. So to kind of conclude on macro-op fusion, you know, we're already with RISC-V fetching fewer dynamic bytes than the other ISAs, and that's being untouched. We're really taking that as an advantage here. The pipeline controlling the data path of the processor can also stay untouched. You're really only having to modify the decoder logic to really take advantage of this. And when we use this, we're going to use less pipeline resources, less issue window slots, fewer register file reads and writes. It's really a pretty cool technique, and the ISA stays the same. And no one's going to notice this unless they're stupid enough to go around and measure instruction counts. They're the only ones that might see something that's a little off. To conclude for the compiler, I actually started out doing this because I assumed that the compiler was terrible, and I wanted to come to you guys and ask you, please make the compiler better. It turns out actually the compiler's doing pretty decent. There's a few places it goes a little wonky that I discussed in the tech report, but basically, the compiler quality is actually pretty good right now. One thing, though, that we do need to address is in order to take advantage of macro-op fusion, we will have to train the compiler to understand what fusion pairs we care about in RISC-V. GCC already knows about fusion. Other ISAs use it. We just have to tell it for RISC-V. So the data that I'm presenting here was assuming that the compiler knew about it and could do better code scheduling. But we'd lose about half of the possibilities because it sometimes likes to split idioms. It likes to split instructions up because it doesn't know that it's supposed to keep them together. For the programmer, basically I'm just going to say, please profile your code. You'd be amazed at what small changes you can make that the compiler can't. That can show a 10, 20% increase. There was one little flub in the compiler that caused the libquantum for RISC-V to be like 20% more than it needs to be, and that's actually just one instruction that happened to be that 20%. And for the architect, RVC, my guess is that that's probably going to be kind of like a de facto standard for RISC-V. It's a really great tool. You know, you don't lose performance. In fact, you'll gain it because you won't have too much pressure on the iCache. Also, I didn't kind of mention this, but overfetching, you know, fetching more than one instruction a cycle, you know, to maybe look for fusion opportunities, that's actually a good idea for energy efficiency. In fact, it's such a good idea. Rocket already does it. It fetches 16 bytes up to 16 bytes a cycle. So don't be afraid to fetch more to look for fusion. And not all solutions require an ISA change. So with that, I think we made a pretty good case for RISC. We can be denser, we can be faster, and the nice thing is, you know, particularly for an open source community, for an open source ISA, any extra complexity is felt by everyone. So with this technique, we can keep the microarchitect can decide how much complexity they want to bite off. And in terms of future work, I give this out to you guys. I'd love to see some more evaluations in terms of new languages, new benchmarks, new runtimes, and I'd like to see what idioms show up in your code. And so with that, I'll yield my time to questions.
Hi, very interesting talk. I was a little surprised. Actually, your conclusion is not very clear to me because we know that micro-op fusion works. I mean, Power has used it, you know, first crack it and then fuse it. So are you making an argument for micro-op fusion, or are you making an argument about ISA?
I'm saying that you should keep the ISA as simple as possible, and you should use macro-op fusion to make your processor go faster without modifying the ISA.
So I'm all for that, right? I mean, because simpler the ISA, easier it is to compile, because compiler doesn't have to worry about so many things. But then I don't understand your argument about space being taken by ISA, I mean, instruction fetched bytes and so on. Because you're not going to mix compressed version and uncompressed version in the same program, right?
The compressed ISA is 2 bytes and 4 bytes interleaved, and there's no alignment requirements. So from that point of view, because thumb 1 was only 2 bytes, so you already kind of, I guess it's already intermixed anyways. And so you can do fusion where you fuse maybe a 2 byte with a 4 byte, or you could do a 4 byte and a 4 byte. You could do any sort of fusion that you're willing to look over.
I see. So you think that by just rearranging things, we can still get back to the same level of byte complexity or something?
What I'm saying is that we
for
already
ISA.
are very dense. So my ideas are not going to change the instruction bytes of a program. We're already really dense. What I'm saying is that we can lower the operation count by fusing instructions.
That I do believe. Yeah. Thank you.
Karthik Swaminathan from IBM. So what is the impact of the GCC version that you were mentioning? I really didn't understand how that can affect.
What amazes me is that as old as GCC is, and some of these ISAs are, every version keeps making the code generation better and better. And
but you were saying it is becoming bigger, becoming worse with the later GCC version. So I wasn't able to understand that.
What is getting worse?
You said that the number of instructions were actually increasing with the GCC
No,
version?
I meant that they're getting better. It's getting lower.
Okay.
If I said otherwise, I misspoke. No, I didn't say everyone should use GCC 4 or something.
Right.
In fact, right as I finished collecting this data, they came out with GCC 6.1.
So you're talking about how you're making a point at how this macro.
Can you introduce yourself, please?
Jonathan Backrack, Berkeley. You're making a stronger argument for the beauty of the compressed instructions. What I worry about, and now you're seeing how you can exploit it. What I'm worried about is that you have compressed and uncompressed binaries. It seems like you should just, since it's so good, why don't you just require that everyone do compressed? Because
I think it will, my guess is that RBC, the compressed ISA, may become kind of a de facto standard. People realize this is a really good idea. But, we're not quite there yet. We don't really quite know exactly all the complexities. I work in the boom processor. I suspect that adding RBC could quite add another stage to the code just because I'm so tight on it. So I guess it's not something that we're ready yet as a community to pull the trigger on and make that a requirement. Or saying that that's the general purpose ISA, but maybe.
Well, since there's just all this work on having one binary, right? It just seems like you should try to have the fewest number of formats there.
Yeah, so the ISA was designed to be modular. There are applications where you definitely don't want C. You might be designing a little accelerator. Code size is not a problem, and you don't want to deal with variable length. However, I think for, say, Linux shrink wrap binaries is probably likely you would, Linux systems would probably want G and C, and probably V when we do the vector one. So I imagine, Linux ABI. So it's very important to get clear in your head the difference between ABI and these ISA modules. So for a given domain, people are going to define a standard ABI, and they probably will pick C as part of those standard ABIs. That doesn't mean we shouldn't continue to support systems that only have the uncompressed, because I think they'll still remain important for lots of embedded things. And also for teaching. When I teach a class, I want a toolchain that works without the variable length stuff, because it's much easier to teach the stuff with that. So there's lots of use cases where you don't want to mandate, that's why it's a separate module. That was a deliberate part of the design. But for most ABIs, yes, you should be part of the ABI.
Michael Broder, I'm unaffiliated. You mentioned at the end there about new languages for the platform. You talk about programming languages. So the reason I wanted to talk about that is I went to the GitHub page for Rust, and I asked them to try to see if they could figure out how to add RISC-V support. And then Alex Creighton said we needed to upstream our LLVM changes for RISC-V. So I opened up a ticket on that repo. And then I think another user posted a comment that they were getting some issues with some instructions and trying to compile Rust. So who would be the person to direct that to make sure we get that working? Okay. Thank you.
Hey, Michael Pallauer, NVIDIA. So, how does macro-op fusion interact with things like precise interrupts or faults? Like if I fuse two loads and the first load faults, how does that show up?
Munir from Northrop Grumman. You mentioned early in the presentation that x86, where it decodes the instruction to micro-ops. Now the fusion is now going back kind of to the sys type instruction. Does it complicate the decode logic in the pipeline? Correct.
fire a control signal that this is what's going on. So I really don't think it's that complicated. I think the hardest part is making sure that you get the exception behavior correct. But at least if you're just fusing like integer stuff that's not going to accept, I don't think it's that complicated. But that'd be fun to quantify. And speaking of that, I accept pull requests to Boom. So if someone wants to add this, they could definitely try it out. Thank you.
Awesome. Thanks, Chris.